Hello, we are Team MIST Mongol Barota from Bangladesh, ready to jump into the University Rover Challenge 2023 with our highly advanced rover, Phoenix 3.0. Welcome to our System Acceptance Review for URC 2023. This year, we have re-engineered our previous rover, Phoenix 2.0, to accede to the provided competition missions, incorporating newer technologies with a workforce of more than 50 students. The core architecture of Phoenix 3.0 is divided into three modules: the body, arm, and science. The rover's body consists of a modular chassis made of stainless steel and rocker bogie suspension with a bevel gear differential mechanism to withstand both frontal and rear impacts during its venture into the rocky terrains. The mobility system of Phoenix 3.0 is implemented using a steerable wheel system composed of customized 3D printed honeycomb-structured, non-pneumatic wheels made of thermoplastic polyurethane material. The 2 degrees of freedom wheels are capable of rotational and steering movement, allowing comfortable movement through tight spaces or along straight lines. Our Phoenix 3.0 has a 5 degrees of freedom articulated arm with the capability of performing a wide range of dexterity tasks given in the equipment servicing mission. Keeping in mind the weight issues of our previous rover, this year we have used a chain-driven base instead of the belt-driven base in the arm gripper and implemented 4 carbon fiber links instead of 2 aluminum links due to its high strength-to-weight ratio. Moreover, to facilitate pitching and rolling motion, we have used a bevel gear mechanism to actuate the end effector grippers and a worm gear mechanism to grip objects up to 5.12 inches wide with strength and precision. Our rover arm is not only capable of a strict grip and easy maneuverability, but also performing equipment servicing tasks such as lifting payloads weighing more than 8 kilograms, opening drawers, pushing buttons, switches, and knobs. The components of our rover are controlled by new iterations of our customized PCBs in the electrical subsystem. The chassis houses the modular layout of the electrical components, which supply ample power to the core system using LiPo batteries. Other electrical components integrated into the rover include sensors to detect system temperature and battery voltage. In the event of operational issues, we have included a visible kill switch for emergency shutdown of the rover, as well as a fail-safe protocol for remote deactivation. For autonomous navigation missions, we have taken several steps to ensure the precise orientation of our rover. This year, we have used odometry and computer vision for strategic path planning and smoother traversal. For improved navigation and localization, we have integrated 10 DOF IMU sensors with the GPS module, which provides reliable GPS streams. The data received by onboard IMU sensors and GPS are fused by Kalman filter, providing higher precision and accuracy of the rover's actual location. A custom script publishes the sensor data in ROS to navigate to the visual markers. Phoenix 3.0 uses a LiDAR and Z2 cameras controlled through Jetson Xavier NX. For identification of air tags up to 5 to 10 meter distance, our rover uses a combination of 2D pose estimation and multi-marker detection. 3 LEDs have been integrated into the rover to indicate successful arrival to the destination or completion of a mission. In order to ensure optimal communication between the rover and the base station, we have integrated multiple distinct channels for control, backup control, and data transmission. Our primary control channel operates on a 2.4 GHz band with a secondary 900 MHz channel serving as a backup. To facilitate data transmission, we have allocated 2 independent channels of 5 GHz and 1.2 GHz for the FPV cameras, while an additional 3 cameras for science or sensory data feedback utilize a common 5 GHz channel. This time, to collect soil samples, we have developed an action module that makes this task faster, more efficient, and more precise than ever before. On the rear of the rover, there is a testing chamber that is equipped to identify biomolecules found in the samples of rock and soil. The suction module is composed of an actuator and 3 pumps that work in perfect synchronization to extract soil samples from the ground. A drill is also attached in case of hard soil samples to soften it. The suction samples are deposited through separate funnels to the beakers attached to the customized beaker tray in the testing chamber for each of the corresponding soil tests to avoid cross-contamination. A heating pad is also used to provide heat to the beaker of the necessary tests. The biomolecules in the sample are identified through multiple chemical tests, including Benedict's solution for carbohydrate test, Biuret test for protein detection, and ion test for ammonia detection. And we are also working on the luciferin test to detect ATP. The outcomes are instantly monitored through the base station for prompt assessment and fed into our personalized algorithm. Based on predetermined criteria, the samples are categorized as extinct, extant, or no presence of life. Using an USB microscope with MVOC sensor, we can detect even the smallest signs of life. Our custom database of nearly 1,000 rock samples and neural network models with transfer learning has allowed us to predict and identify fossilized samples with 97.3% accuracy. We also use a Munsell chart to estimate the level of organic carbons in the rocks. This year, we will expand our analysis to a wider range of rock samples compared to last year, which will give us a larger dataset of newer samples. As a part of our educational outreach plan, we have hosted several workshops and plan to host more seminars and conferences in the near future. As the finals approach, we plan to maintain our rover serviceability by undergoing several mock missions as we expect in the main competition. We, MIST Mongol Barota, are confident in our capability and effort. Thank you for your consideration. MIST Mongol Barota wishes good luck to all participating teams. Thank you.